Hello friends, welcome to our channel Crash Course for the Engineers. In continuation with the quest for learning, we in today's session we'll talk about the basics of refrigeration. Now, these are the basics which are very simple to understand, and in most of the theory numerical problems will need these basics. So, let us talk. Let us start with a very important thing, which is called as the enthalpy. Now, in case of the uh, refrigeration, we many of the times or most of the times use this enthalpy term. Now, this enthalpy is nothing but the total heat, is the total heat content content of. Now, refrigeration systems have the refrigerants working as a working fluid, so the total heat content of the refrigerant. Now, this H is equal to U plus PV, where U is the internal energy, the P is the pressure, V is the velocity. Now, how we use this enthalpy in case of the refrigeration? Now, these enthalpy values are used to find out the energy calculations. For example, the work input to the compressor, heat rejected by the condenser, then heat absorbed in the evaporator, etc. Next, very important thing that we need to understand is the pressure enthalpy enthalpy diagram. Now, in case of the refrigeration systems, we use two types of diagrams. First is the pressure enthalpy diagram, and second is the temperature entropy diagram. These two serve different purposes. Now, this pressure enthalpy diagram, uh, called as the pH diagram, is the graphical plot in which we have there are two axes, so x-axis and y-axis. So on x-axis, the value of enthalpy is given in terms of kilojoule per kilogram, and on y-axis we have the pressure term, which is given in bar or kilopascal. Now understand, friends, every refrigerant is having different kind of enthalpy diagram. Uh, we show the refrigeration cycle. The refrigeration cycle we are talking about here is the vapor compression cycle. So suppose if we talk about the vapor compression compression cycle, and in the system if we are using R134A as refrigerant, so suppose this is our pH diagram. This is the dome. Okay, so if the refrigerant is dry saturated at the end of the evaporation, so suppose this is your process of compression, then there will be two dash, then this three, then four, and four to one. Now suppose now this is the uh, vapor compression cycle uh, in case of the R134A. With there are some assumptions that we will not talk about. So this pH chart, so this pressure enthalpy chart is used to show the cycle uh, in a organized way. Now, friends, understand that as I told you, with this pressure enthalpy diagram, we use one more diagram. That diagram is called as the TS diagram because it is called as the temperature entropy diagram, and we say it as a TS diagram. Now, it is of the same purpose to show the refrigeration cycle, but some of the processes of refrigeration cycle cannot be shown on the temperature pressure enthalpy diagram. So, to show it in a correct way, we need the temperature entropy diagram. Now, the units will be temperature uh, is given in degree Celsius or Kelvin. Now, friends, understand that suppose this is the dome. Uh, as I told you, let us start. The refrigerant is dry saturated at the end of expansion, uh, at the end of evaporation. Now, we say that the process of compression is isentropic. So this is 2. Then the temperature drops to dash. This is 3. Then there will be a dotted line and there will be this is the 4. So on the basis of some of the assumptions, using some of the assumptions, I have plotted the diagram for the temperature entropy diagram for uh, a simple vapor compression cycle. Vapor compression cycle with some of the assumptions. Now we'll go to the next term, which is related to the refrigeration systems, which is called as a term of refrigeration. Now this term of refrigeration is denoted by TR. Now, friends, understand that the purpose of the refrigeration system is to remove the heat from the refrigerator or the working environment. Now, what is the turn of refrigeration? It is the cooling capacity capacity required, required to maintain maintain temperature of 1,000 kilogram or 1 TR of water from and at 0 degree Celsius for 24 hours. Now, friends, understand that for this kind of refrigeration, you will find his definition, and all the definitions are correct. In the essence of the definitions is very simple. We want to maintain the temperature of water for at 0 degree Celsius for the period of 24 hours, and the quantity of water is 1,000 kilogram. So how much heat is required to be removed from this will be the turn of refrigeration. Now this 1 TR, it was calculated. So 1 TR is equal to 3.517 kilowatt, or it is equal to 211 kilojoule per minute. Right. So These are the sample values. These are the values for 1 ton of refrigeration that we get by some calculation. Okay. Now, friends, our next term that we need to understand is called as that there is a term which is similar to the efficiency. When we talk about the refrigeration system, we don't have the term which is called as the efficiency, so we have the coefficient of performance. Means- So it is called as a COP. Now, what is the COP? COP is equal to, it is a ratio of Q that is absorbed from the refrigeration system by the refrigeration system divided by the work input to the system. Now, this heat absorb takes place in the evaporator, so it is also called as the cooling effect, cooling or refrigeration effect divided by the work input. Both of these terms should be in uh, kilojoule per kilogram. So we'll get the coefficient of performance. It is dimensionless quantity. Now understand, friends, more the COP, good will be the system, uh, better will be the system, better will be the efficiency of the system. Uh, Now there are two terms which comes into picture when we talk about the coefficient of performance. First is this refrigeration effect and second is the work input. Now let's talk about the refrigeration effect. It is also shown, it is written as RE. So what is this effect is the amount of heat absorbed or removed from required area from required area. Now, friends, I have plotted the simple compression cycle VCC just 1 minute back. So let's go to the diagram. There are two things. So uh, I hope you can see the diagram. Now, if we talk about the RE, okay, so RE is equal to H1 minus H4. This this line tells us about the RE. If the length of this line is bigger, the refrigeration effect will be more. If the length of this line is small, the refrigeration effect will be lesser. Now, uh, uh, as I told you, the RE tells us the capacity of the system, heat removal capacity of the system. Uh, Let us talk about the next term, which is called as the work input, small w. Now, this we know that when we are talking about the refrigeration system, vapor compression refrigeration system, the work input is given to the compressor. So, mechanical energy input to the compressor can be called as the work input. So, mechanical energy input to compressor. Okay, let's go back to our diagram. So if we talk about this pH diagram, the compression is shown by the process 1 to 2. So small w is equal to H2 minus 0. The length of the line. 1 to 2 tells us whether the work input to the compressor is bigger or work input to the compressor is smaller. Now, uh, there is there is one more term which is called as the heat rejected. Heat rejected. Now, heat rejected is always shown by QR. Now, what is this heat rejected? It is the heat rejected or expelled to the surrounding during the process of condensation. So, friends, this heat rejected is heat. Okay, just a minute. Yes, is the amount of heat rejected to atmosphere or cooling medium during condensation. Let us go back to our diagram. So, what we told this process 2 to 3. The process 2 to 3 is the heat rejected during the process of condensation. So, Q R is equal to H2 minus H3. Now, more the heat rejected, the bigger size needed for the condenser, and smaller the heat rejected, smaller size of the condenser is required. Now, friends, let us go back to our cycle. Uh, I'll draw the cycle, vapor compression cycle. Just a second, and I'll explain in short two important. Sorry, sorry for inconvenience. I click something, so yes, everything is fine now. So this is the pH and this is the pH. Okay, so pH and P. So this may be the dome, and in this case, this may be the dome. Okay, so these two terms that I am discussing here is called as one is called as the subcooling, and second is called as the superheating. Now, this is our cycle that I have explained to you. I have told to you. Okay, so one, two, three, four, one, two, three, four. Now, what we are doing in case of subcooling? We are cooling the refrigerant after the process of condensation. So there will be some process, there will something will happen after 3, so up to 3 dash. So 3 to 3 dash is called as the subcooling process. So now I can uh, revise this cycle in a different way. So okay, so 4 will change to 4 dash. Okay, so the RE value will be equal to 4 1 sorry refrigeration effect will be H1 minus H4 dash. Previously, it was H1 minus H4. The length of the line is more. It means that more heat is absorbed in the evaporator. It means that the system is absorbing more heat, keeping the work input same. Okay, so this is called as the subcooling process. Uh, it means that the COP will increase in case of the subcooling. Uh, I can show the subcooling on the TS diagram also. So this uh, 3 to 3 dash and this will be the 4 dash. I hope that friends you are understanding the things. Uh, Next term is called as the superheating. Let us talk about the superheating. I'll start with a fresh diagram so that you'll understand it. Otherwise, there may be some confusion. Okay, so this is our pH diagram and this is our PS, pressure, enthalpy, temperature, entropy. So, okay, now let us draw the cycle. Okay, so this was the original cycle with the red. This is the original cycle with the red. Okay, so 1, 2, 3, 4, 1, 2, 3, 4. Understand, friends? This 3 to 4 line should be dotted in case of TS diagram. Okay, why? I'll explain it in some of the video. Now we are talking about the subcooling process. Let us go. Let us change the color. We are okay. So this subcooling process is taking place after this point one. We are increasing the temperature of the refrigerant after the in the evaporator, so that the refrigerant which is leaving the evaporator is uh, in a dry state. Why we are doing this thing? Because uh, we want that the refrigerant should be in a vapor phase when it enters into the compressor. Okay, so this will be our one dash and this will be our two. And everything will remain the same. Okay, if everything is remaining the same. Now, what what we can say here, uh, this superheating superheating is 1 to 1 dash on the pH diagram. What will be the effect of this superheating on COP? We will discuss in the lectures. So for that you need to watch the lectures. Okay. On TS diagram, it can be shown in a different way because uh, this is the increase in the temperature. Okay. So this is one dash. This is one. Here it is two dash, and here it is uh, two double dash. If I am keeping everything common, so this will be the cycle. So on TS diagram, it will be in a different way. So 1 to 1 dash is the increase in the temperature of the refrigerant after the evaporator. Now, friends, I hope that you are understanding the concept that I am covering during the sessions, various sessions I am covering. So, if you are liking the videos, please subscribe the channel. Please like the video. It gives me more motivation to post videos related to the uh, refrigeration air conditioner. Okay. If you have any concept related issues, please put it in the chat box so that we can discuss it and I hope that I uh, will give the solution to your question. Thank you, friends. Thank you for watching the video.